So good morning, everybody. Can you hear me? Can someone answer to me? Okay, that's great. Okay. So first of all, right, so welcome you all to join this class. Okay, so it's my great pleasure to be your lecturers in this semester for these subjects. Okay, first of all, so let's have a brief introduction of these lectures. So this is a combined lectures of the BSE 2122 and 1101 electric teleology and electric fundamentals. Okay, between the bachelor degree students and high degree students together. So we have separate tutorial sessions arranged, but lectures we combine together. So as I show here, so we have the lectures, combined lectures, okay, on Thursday, okay, from 9:30 to 11:30, okay. So, which for the whole subjects will be conducted online. No face-to-face lectures arranged at this moment. For the tutorial sessions, you see here. So, originally, we have 3 sessions of tutorials. For the BEng students, on Tuesday morning from 9:30 to 10:30, so 1-hour sessions. On Tuesday afternoon from 5:30 to 6:30 p.m. for the high D students, Group A. And on Thursday noon, 12:30 to 13:30 Thursday for high D Group B. But since this is online tutorial sessions, okay, so not face-to-face tutorial sessions, I might propose that to cancel. So to cancel this group, okay, of the online sessions. Okay, we cancel this one. So we just have 2 sessions of the tutorials. So one is done on the Tuesday morning from 9:30 to 10:30. The second one in the Tuesday afternoon from 5:30 to 6:30. Okay, so both the BEng students and high D students, okay, can attend, okay, either the morning session or the afternoon sessions. Depends on you. Okay. Meantime, for each of the lectures and the tutorials, I will take the records of it, and you all can download the radios, okay, after lectures or tutorials onto your local computers for revisions. So if you have some urgent things that cannot attend at the live lectures or tutorial sessions, okay, so you can download the videos from the Blackboard. Okay, you can slowly to review of it. Okay, and I know that the online lectures is slightly different from the face-to-face lectures. Okay, so if you can have some questions during my lectures, you can raise your hand, or you can write down that via the chat box. Okay, via the chat box, so that I can timely understanding. So what things you are not good at. And during tutorial sessions, you also encouraged to raise questions during the tutorial sessions. You write down, you voice out. It's okay. Okay, don't hesitate to do that. Okay, try to interrupt me, right? So by raising questions, because this is a remote, mode study. I don't know. Okay, so by eye contacts to know what you have the questions about it. So anyway, remember in the teaching schemes, right? I write down that we have tutorial sessions on Thursday noon. But this is online tutorial sessions. I suppose to cancel the one on Thursday noon. We just keep the one in the morning of the Tuesday and that in the afternoon of the Tuesday. So I once again remind all of the Heidi students to choose attend either the morning session tutorial or the afternoon session tutorial on Tuesday. Okay. So later on, I will clarify this point by writing an email to all of you so that no students miss these informations about it. And so for the contents of these subjects, so mainly we focus on the following 5 chapters, but not limited to it. Sometimes I get to attend some of the additional contents to you for your good understanding of these 5 topics. So the chapter 1, we are talking about the direct current systems. So namely, so in short, DC systems. Okay, so some of you already touched about the DC circuits. Okay, some of you already learned some physics during your high school, middle school, right? You learn about the DC circuit. You know about the voltage. You know about the currents. You know about the resistance. But that is the most simple circuits issues, not touch the natures of the electricity issues. So in chapter 1, we will have look at the DC systems. We will slow down the pace in chapter 1 so that all of you can get used to the study of these subjects by studying the chapter 1. And the chapter 2, electromagnetic circuits. So simply speaking, the chapter 2 is about the magnetic circuit. Magnetic circuit. So you know that we have the magnet in practice. You have so-called magnetic field. Magnetic field. So how the magnetic field be produced? How does the magnetic field change with the electric currents? Where and how use the magnetic field will be taught in chapter 2. So chapter 2 is a new things to most of you. I'm not sure, right? So because some of you comes from the associate degree or some of you may have learned some of the contents on the magnetic field, but most of you maybe have no more knowledge on the magnetic field. So the concept in these chapters a little bit difficult for some of you to understanding. So we will take a little bit longer times to talking about the electromagnetic circuits. So this is the electromagnetic circuits. After that, we were talking about the single phase alternating circuits, current circuits. So which in short, AC circuits. Chapter 1 is the DC circuits. Chapter 3 is the AC circuits. Why we put the chapter 2 electromagnetic circuit before the alternating circuit? Because the single phase alternating current circuits actually involves electromagnetic circuits. we use the magnetic field together with the mechanical force to generate electricity. Okay, the keywords, we use magnetic field, plus mechanical force to generate electricity. That is the single phase alternating current circuits. Okay, so in addition to the single phase AC circuits, in chapter 4, we have the three-phase AC systems, which in general be the big generators generated electricity in power plant. So in a power plant, so the electricity that we use now be generated in the power plant in three-phase, not single phase. Okay. So chapter 4, after that, we touch about the electric machines. The first one is the single phase transformer. Okay. So of course, after this subjects, we have another subject in the next year semester. We talking about the powers and machines. So single phase transformer here serves as a starting of the powers and machines. Okay, starting power machines. Okay, that's the contents to be taught in these semesters in these subjects. In addition to the lectures and the tutorials, we also arranged 2 experiments. Originally, these 2 experiments are required to carry out in labs in face-to-face mode. But as you know, due to the COVID-19, we cannot carry out this in the labs. So this year, we ask the tutors to take videos of their experiments and then post these 2 videos onto the blackboard. Then you too, so you all are asked to watch these 2 videos and refer to the laboratory sheet, laboratory sheet. Then to choose one to write a formal report, and submit the formal report onto the blackboard. So in due course, the coordinators, Dr. Hilda, will send email to you, tell you how to submit the report. Okay, so if you still have some of the questions about laboratories, you may contact with the Dr. Hilda, so that you can get details instructions about that. We are very sorry that the experiments cannot be carried out on the campus in labs, but we hope that next semester that all the experiments can be carried out in labs. In that moment, you have the chance to touch the machines related to the electricities. Okay, this is lab works. Now, about the assessments. So most of you, of course, very concerned about the assessments here. The assessments, largely speaking, including 2 parts. One is the so-called final examinations, which taken 60% towards the final grade. It will be a 2 hours take-home examination. So we call it take-home examination because we have no invigilators, right? So the questions will be posted on the blackboard, and you are asked to finish the question papers within 2 hours and upload the answer script onto the blackboard within certain times. Generally, extra 30 minutes will be given you to download and upload the exam questions. Okay, 2 hours for you to answer the questions. Okay, answer questions. This is the final examination arrangements. Because it is open book one and no invigilators there, so you may refer to your teacher notes, refer to tutorial examples, and so on. Okay, but do not copy the things onto the paper, onto the answer script directly. Okay, take a care that they will have some tricks about it. Okay, if you found that you just simply copied some things from the teacher notes or from the tutorial examples, you will be get 0 mark. Okay, so the marking will be relatively strict. Okay, relatively strict. Okay, so this is the final examination issues. Take care about that. For the continuous assessment, it takes 40% towards the final grade, which including 2 assignments and 1 experimental reports. Assignments. Okay, so 1 assignment will be distributed to you in the middle of the term. Okay, so you will be given 2 more days to complete the assignment and submit on Blackboard. Okay. After the assignment, I will try my best to post the solutions to the assignment onto the Blackboard for you all, for revisions use. So anyway, so all things, we would like to help you to have a good understanding on the contents of these subjects. So here we give you some of the background about why we choosing these subjects as the compulsory subjects to both the HID and BA English students. And first of all, you should know that inside the buildings, we have no facilities using the electricities. So we first have to be an engineer, in the building service engineer, So you have to know about how the electricities, be distributed, and how the electricity be used, and how the electricity, be so guaranteed so that the safety issues, no problems. So and also nowadays, because the high-tech issues, we have note of the facility that using the lower voltage powers also, such as the communication systems, the CCTV systems, even some of the smart facilities that use in the lower voltage, DC voltage or AC voltage. So since we have a lot of the instruments inside the buildings using the electricities, particularly such as the air conditioner systems, the fire warning systems, pumping systems, even the heaters or whatever computers, we using the electricities inside the buildings. So the safety issues is the first issues. So in using the electricity, safety first, functionality second. So in next year, you have subjects that concern about the safeties of the usage of the electricities. Okay, So in addition to the electricity distribution and utilizations, we have to know about the performance of the equipment using electricity. So how the equipment be controlled, and what is the performance of the equipment at the moment of starting, at the moment of the running, at the moment of braking. So their performance will be different. Their usage of electricity will also be different. We have to know all of this. Okay. So yeah, serves as the fundamentals. These subjects give you the basic concepts and issues about the usage of the electricity in the buildings. Okay, so someone might ask that why we should use the electricity inside the buildings. Why don't we use in the other types of energies? Of course, nowadays we using the other type of energies, but the 90% of energies we use in the building still be electricities. Okay, that's because that the electricity is clear for the buildings. Okay, it does not produce carbon dioxide, does not produce waste, okay, does not produce pollutants. Second point is that the electricity is powerful. Okay, it can be distributed, okay, in high voltage supplies. Okay, so not just in the low voltage, but also in high voltage supplies. Okay. The third point is that the electricity can be distributed simply. You're thinking that the gas, the water, that should be distributed carefully using the pipes. Okay, the pipes. But the electricity distribution is very simple. They use the conductors. Okay, and also easy to control. Easy to control. Okay, you just using the switch on and off. Okay, the electricities, making it easy to control. For the water, okay, if you want to control it, you should pay attention to the water pressures, So you can using the valves to stop the waters at one points, but the other points still have the waters be there. Okay, if they have leakage, they are a big pressures push the waters outside. But electricity is not. For a circuit, if this circuit is open, there is no electricity on that circuit. And also, lastly, it is easy to detect the abnormalities. Okay, so when there is a accident, occurred along the circuits, so we can easily detect this one using some equipment, so that we can solve it quickly. So that's why we are using electricity inside the buildings. So how and what we have to learn. So the purpose of learning the electric subjects is to, one, to know the facilities control, the characteristics and running and starting of the machine, because this is one thing that we have to learn. We do not learn more about the physics behind the electricity. We know how to control, how to understanding the characteristics of the running and starting of given machines. And second point, we learn how to test or to verify the machine's performance, and to learn how to represent in so-called equivalent circuit the machines, so that we can analyze the performance and therefore to suggest improvements on the performance of the machines. Okay, so the second point is that to learn how to test the machines, learn how to represent the machines using the knowledge you learned in terms of the equivalent circuit. Okay, so that's the purpose. And to achieve that purpose, you have step by step understanding, one, the elementary electric components. Okay, so when you're trying to represent equipment, so how to represent the equipment? We have several elementary electric components, namely, as you said now, okay, as you know now, the voltage, current, okay, resistance. Later on, you will also learn about the capacitance, okay, inductance, impedance, and so on. Okay, many components that makes this circuit. Okay, so the second point, you should know how to draw an equivalent circuit for a given machine. Okay, so here, okay, equipment circuits, concept equipment circuit. So equipment, each of the equipments, for example, the lights, the computer, the heater, okay, the cleaner, okay, the fan, all these machines can be represented by one or two, okay, electric components in a circuit. Okay, in a circuit. And the third, you should learn how the electric source be arranged and what is the properties of the electricity source. Fourth, okay, so we will talk about the electric circuit basic theories. So you draw a circuit with different electric components, namely the voltage, currents, resistance, and so on. What's the relationships between the currents, voltage, resistance? What's the so-called power consumptions of the instruments? What is the efficiencies of the instruments? What's the voltage drops across the machines, and so on? How much is the magnetic field produced? Okay, how does the magnetic field affect the performance of the machines? How does the magnetic field stabilize the machine's operations, and so on? Okay, so all this will be introduced to you during these lectures. So many concepts. Okay, so to help you to have a all-round understanding about electricity usage in the buildings. Okay, so we have three-stage arrangements about electric circuits in these programs. So the stage one, fundamental theories and principles, that's the subject of this subject serves for. The stage two, many applications of fundamentals able to design general services. This is the stage two, subjects. Okay, next subjects we are made on this one. Next two subjects made on this one. One is the power and machine. The other one is the electric installations for the BNG students. Okay, for the RD students, so that two has been combined together, which will be the electric installation, two or something like that. Okay. Stage three, integrated design to a particular buildings. So this will be carried out while the final year research project and design projects. Okay, So in that case, giving examples of buildings, okay, to our 3 students, okay, I grouped together to design whole systems for the buildings, including the water supply systems, including air conditioner systems, including the electricity supplier systems. That is stage 3. So after that, after graduations, you are able to design the building systems for a given buildings. Okay, you are directly be able to work on the projects. So how to learn? So generally, the approach of studying is the systematic one. System approach. So when we're talking about each of the components, we first give you examples of the systems. Then based on that systems, to talking about each components, so that you have a good understanding of the relationships between each of the electric components. To see how does each components related to the works of the systems. And meanwhile, so we have many assumptions. So to simplify the systems, actually in practice the systems may be more complicated because there are many uncertainties during the writings of systems. So to make the things be simple, sometimes we given some assumptions. Of course, once you have the assumptions, we mean that we ignore some of factors affect performance systems. So you should understanding the limitations of each of the assumptions. Okay. Lastly, since the time limitations, so we can note talking so much about the theories behind each of the concepts. Of course, I will try my best to explain to you the basic principles behind each of the concepts, but not so details. If you still are interested in the theories behind each of the concepts, I'll give you some hints, and then you can dig into deep issues by yourselves. So your fix is that learn how to use of them rather than how they can be created, how they be invented. Okay, so this is introductions of these subjects. So telling you why we have to learn about these subjects, how we arrange the study of these subjects, and what we have to learn about these subjects, and what's the approach of study of these subjects. Okay, so anyway, take it easy about learning about these subjects. I fully understanding that some of the contents in the subjects is a little bit difficult to some of you, not of you, not all of you. Some of you very smart, some of you. But anyway, take it easy about that. We do not want to make difficulties to all of you. We just want to help you to learn as much as you can about the usage of the electricities. Okay, this is a brief introductions about the subject itself. So now we come into the chapter 1, talking about the DC systems. Okay, now we come into the chapter 1, direct current systems. In short, DC systems. So now you understand, okay, what's the meaning of the DC systems, namely direct current systems. What does it mean by direct current systems? Direct means straightforward, right? Straightforward means that one directions. Okay, one directions. Okay, just like you're working on the street, one direction. So straightforward. So direct current means that the voltage itself, the directions of voltage, the current of the voltage, okay, the same, keeps the same, keeps same directions, no direction change. Okay. In terms of electricity, no polarity change. Positive is positive, always be positive. Negative side always be negative side. Positive always be positive side. That's the meanings of the DC systems. So I would like to correct one of some concepts that DC systems does not mean that the voltage keeps no change. Does not mean. DC systems means that the voltage keeps the same directions. For example, positive 5 volts, positive 4 volts, positive 3 volts, and so on. Okay. But not, right, change the directions. That's the meaning of it. Okay. The contents of these subjects, or we say the arrangements of the slides of these subjects. Oh, these chapters. Chapter 1. First, so we talk about the simple DC systems to show you about the simple DC circuits. Okay. And then we will talk about the load characteristics. So what kind of load, or we say what kind of instruments using the DC electricities, and what's the properties of the user. The load here is the user. And the third one, so we will introduce you several useful circuit theories. Okay, so the theories is, right, proposed by some researchers to describe the relationships between the different components in the circuit. And in practice, we have different types of the operations of electricities. So 3 cases be raised here. Parallel operations. The parallel operations means that in practice, sometimes we arrange the source connected in parallel to provide powers to heavy load. Okay, some of load very heavy. They use big powers. Single source is not enough to provide power to it. We can use 2 sources in parallel to share the burden. Okay, that is the parallel operations. Sometimes we supply the electricity to users using the so-called radial circuits. Most of the electricity be supplied in a radial circuit way. We will talk about, okay, the characteristics of the performance of the radial circuits. In addition to these 2, we have so-called ring circuits. So the performance of ring circuits. Okay, so what's the difference between the ring circuits and the radial circuits? We have several examples to show you how to analyze the performance of the ring circuits. For safety issues, we will also talk about the short circuit analysis. In practice, you may always hear such a concept, short circuit. Okay, short circuit. What does it mean by the short circuit? Okay, how the short circuit can be analyzed. How to protect against the short circuit. Okay. Lastly, we will talk about, in practice, how the DC source be arranged. So as I just mentioned a few minutes ago, so in most of the cases, the electricities, particularly the powerful electricities, be produced in the AC mode. But in many machines, we use it as a DC. How does the DC be arranged? How does the DC source be produced? Okay, we have a short talk about this one. So that's the arrangement of these chapters. Okay, in following slides, okay, we have the slides, okay, by slides talking about these contents. We start, okay, systematically. Okay, as I said, okay, we study these subjects in a systematic approach. So before talking about each concept, let's have an overall outline, okay, about these chapters. These chapters, DC circuits. First, we will give you some examples of the DC circuits. In the circuits, there is a very important, right, components. That's the resistors. In the DC circuits, all users can be represented by the resistors. So the resistors in the DC circuits, okay, means the consumer, power consumer. Okay, the resistors represents the user. The resistors represents the load. The resistors represents the consumer. The powers consumed by resistor. And how the powers be used by the resistor depends on the currents. So we have the currents. Okay, so the resistor can be one resistor, two resistor, three resistor, and so on. So the resistors combinations, that is the network, resistor network. Okay, so the resistor consumes the powers, and the powers provided by a source. The source represented by 1, the voltage, 2, the charge storage. The voltage push the charge flows into the resistors. That's the currents. Okay, so at least we have 3 components here. Voltage, that represents the source. Currents, that represents the power flows. Resistors, that represents the power consumers. So what's the relationship between the voltage, currents, and the resistors? That's the Ohm's law. So Ohm's law describes the relationship between the voltage, current, and the resistors. And onto the resistor, how much powers be consumed by resistors? So we introduce the power concepts. So we will introduce to you what does it mean by the powers. And also to analyze the systems, we have the so-called voltage law. So the voltage should follow some of the laws, some laws. So the voltage follow the voltage law. And we have the current law. So the current follow the current law. The voltage, current, resistor together follow the Ohm's law. The Ohm's law. Of course, we will talk in detail where we're talking about each concepts there. Okay, so when we're talking about powers, we will tell about talking about the batteries and the power supplies and so on. Okay, that is the of course issues. So this is the fundamental. Then we were talking about the measurements of the three components. So we say we have the resistance, we have the voltage, we have the currents. They follows the Ohm's law, they follows the voltage law, they follows the current law. But how to measure the voltage, how to measure the currents, how to detect the resistance. So we have several instruments that to detect the voltage, detect the currents, namely the voltmeters that are used to measure the voltage across a given component. That's the namely ammeters, which used to measure the current through a given component. Pay attention to we use in the wording, voltage across a component and current through a component. Lastly, at the moment of the switch on and switch off of the DC systems, the voltage and current through cross a given component suffers from sudden change. You switch on, you switch off, okay? So the voltage, from 5 volts down to 0 volts, you 1 second. Or switch on the voltage from 0 jump up to 5 volts in 1 second. This we call it transient phenomena. Okay, transient phenomena. Okay, the voltage jump up and down. In that case, you will find that the circuit performance quite different from that of the resistance. In that case, we will introduce you to two new concepts. One is the capacitors. Two is the inductors. The capacitors and inductors take functions when the voltage or current changes. If the voltage and current no change, then the capacitors and the inductors disappear. So they have no functions on the stable current and voltage. While the resistors take functions for whatever voltage and currents. Okay, so this is a network talking, a systematic talking about these chapters. So we will starting about examples, then talking about resistors, then talking about resistors combinations, then we're talking about Ohm's law, the power relationship, the voltage law, the current law. We also talking about the voltage measurements, current measurements. Lastly, we're talking about the transient phenomena in the DC circuits. And by that chance, we introduce you the capacitors and the inductors. Okay, so we talk so much about the Okay, relationship between the components we will learning, okay, in these chapters. Okay, now we're starting from simple DC systems to see what components be included in a DC circuit. Now, we're starting using a battery flashlight. I think all of you have used the flashlight in past. Okay, so now if you depunching this right flashlight, open it, you will find that they have at least 4 components, functional components. Okay, functional components. The first one is the battery. We call it electricity source. The second one is the conductors that connect the source to the users, the bulb. Okay, the bulb. So bulb is the load, is the consumer, is the user. It uses the electricity, okay, to light up our lives. Between the connectors from the battery to the bulb, we have the so-called control systems that switch on off. So now we have 4 components: source, transmission conductors, control switches, and users load. We can draw the relationships between these 4 components into a circuit like this. Here, the source, that is the battery. Second one is the switch, control systems. The third one is the bulb, the load unit. And the borderline, okay, which is the circle, okay, is a closed loop. Here is the transmission systems, that is wires. Look, here we call this one is conductor. This is the one conductor. You now noticed that the conductors connect the source to the bulb in a loop, closed loop. So this is a healthy circuit. So a healthy circuit should be a closed loop. Should be a closed loop. Okay, so we have the electrical charges of particles. And a charge goes out, a positive electric charge goes out from the source, from here, go right into the bulbs, okay, leading to lightings, and it goes out from bulbs, get into the batteries again. Okay, batteries again. Okay, so actually the batteries does not lose the charge. Okay, so the lightings get powers from the movements of the electrons go through the bulbs. But what lost here? So the power source lost what? Lost separations of the electric charge. Inside the batteries, here on the upper side, for example, just an example, they have positive charges accelerated here. Their positive side accumulated here. They have the negative charge on the bottom of it. There is a chemical force maintain the separations of the positive charges and the negative charges. So positive charge upper, negative charge lower, and separation maintained by a kind of force. okay, kind of force. So this separation itself is energy, okay. And then the electrons moves from this side into the bulbs and back into the negative side. So neutralized with the negative one. So the separation of the charges here, okay, disappeared. That means the energy that maintained the separations here disappeared. And the energy becomes the movements of the electrons. And the movements of the electrons, okay, collide with the particles in the bulbs, produce heatings, and therefore lightings. Okay? So now you should understanding, although that the electrons, you cannot see the electrons. So the movements of the electrons is the energy. Just like the movements of the objects, okay, is the mechanical energy. Okay, just like a bullet. Okay. Okay. So this is the so-called simple DC systems. Generally, we using the voltage represent the source. We using the resistance represent the load. We using the current flows. Okay. So we using the so-called voltage represent the source capability. We using the current to represent how much power flows into the load. We using the resistance represent the characteristics of the load. Generally, all conductors, all components in a system has resistance. So I would like to emphasize that, okay, although we draw that a simple circuit for the flashlight like this, in practice, we using the so-called voltage represent the source capabilities. We using the resistors represent the load unit. We using the current to represent how much energy, okay, goes through the batteries. So all components have resistance. The batteries has internal resistance. The conductors has the resistance. Okay, the resistor, okay, the user has resistance. That's why the new batteries has small internal resistance. Old batteries has big internal resistance. That's why you guys using the mobile phones and charging your mobile phone batteries every day. You found new batteries, you can charge it quickly, and the battery can use longer. For the old batteries, because it has a bigger internal resistance. So when you charge the batteries, the resistance making the charging current smaller. When you use the batteries, the internal resistance of batteries consume powers, making voltage drop. So making that the output voltage to your mobile phones be much lower than the battery itself. Okay, so the resistance is equivalent concepts, okay, equivalent concept that to present the capabilities of okay, components go through the current. When the battery getting load and load, it right chemical force to separate the charge become weak and weak, So it cannot outputs bigger current and short moment. As a result, okay, its internal resistance becomes bigger. Okay. Now anyway, so the concepts of voltage, current, and resistance is equivalent concepts. If you are the first researchers working on the electricity, you can define different concepts. Get the points. So this is just a human being's logic, right? So the first, right, researchers supposed to using the so-called voltage to represent the source. Then the follower, all the other researchers follow these researchers to use the concepts of voltage. Okay, and so does the currents, so does the resistance. Okay. But whether these three concepts represent the natures of the electricity is another issue. But now we already begin to using this logic, right, to analyze the circuits. Okay, we found that such a logic analysis of the circuit will help us to predict the system's performance, to help us to solve the performance of the systems. That's it. Okay. That's it. So now you're understanding that the researchers, the concepts, new concept is not a mystery. It's just an arbitrarily introduced one. So which can be better used to solve the practical problems, which will be the best theory. Okay, here we give you examples of different types of DC circuits. Okay, so here we have the batteries. Okay, batteries. The batteries has positive polarities and negative polarities. Longer horizontal bar represents the positive one. Shorter horizontal bar represents the negative one. Okay, longer positive one, shorter, right? Negative polarities. And the resistance represents the users. Here we have two users in series in the closed loop. It is supposed that the positive charge moves in this way, go through the users back to the negative side. In practice, the positive charge does not move at all. The negative charge, that is the electrons. Okay, in practice, electrons moves. So in practice, electron moves. Electron is negative charge, moves. The positive charge nuclear is not moves at all. Okay, we define the directions. We define the directions of positive charge moving as the current direction. Okay, so here is a parallel circuit. We have one source, two users in parallel connected to the batteries. Now look at here. This is the two-loop circuit. We have one batteries, resistors, another batteries, resistors, another batteries, resistors. So one loop, two loop, three loop. So within this loop, the current in this loop here, the current here, the current here are different. What's the relationship between them? Okay, so, and here we have voltage dividers. So source here, two resistors here, the total voltage be shared by these two resistors. Suppose the total voltage be 10 volts, and these two resistors 1 ohm, 1 ohm. Then the voltage cross this one, okay, is 5 volts. The voltage cross this one is 5 volts. So you have got a 5 volts out from these terminals, two terminals. Okay. This is not one combination of a single source. You have a single source. You have several resistors in different combination. These two in parallel. Okay. Then these two in series. And this, okay, series branch and this branch in parallel. Then in series with this one towards the source. Okay. Okay, so when we're looking at a circuit, we start from this source, look into the circuit. Okay, from the source, look into the circuit. Look into the source. Okay, from source, look into the circuit. Then you can see that these resistors in series with this network. And for this network consists of two branches. One branch, the other branch. In this branch, they have a two in parallel. In this branch, they have a two in series. Okay, so this branch in parallel with this branch, then in series this one. The total resistance should be calculated, okay, based on Seiter, okay, combinations. So later on, we'll talk about how to calculate, okay, the total resistance. Refer to the source. Okay, refer to the source. Now, we're talking about in practice, the batteries. In practice, even batteries, they say they have a voltage 10 volts, but itself has internal resistance, equivalent internal resistance. How much is it? Can be tested. So the internal resistance of the batteries can be tested. Okay, this is the users. We have 1,000 kind of the networks about the DC circuit. The rules or the laws used to solve the networks like this, including Ohm's law. Okay, later on we talk about it. Power relationships, voltage and current laws, Thevenin's laws, superposition and Norton's theorems, and so on. Actually, all of this one so comes from three laws: Ohm's law, voltage law, current law. So Ohm's law comes from the definition of the three concepts. Voltage law comes to the logic of the voltage issues. Current law comes from the logic of current laws. I say logic because human beings logic, right? Okay, for the cows of the animals, they have no such logic. Okay, so we have the Ohm's law be definitions by the researchers. We have the voltage law based on the voltage concepts. We have the current law, and that is based on the current concepts. The Thevenin's law, superposition laws, Norton's theorems are all deducted from the above three laws. So that's why we call it theorems. Laws. You may know the difference between the laws and the theorems, right? The laws means the basic issues we suppose it is. We suppose it is the truth. Okay? Suppose it is the truth. Law is the truth. Law is the truth. Okay? Law is the truth. Relationship is just a kind of relations that we represent some concepts, not a law. Okay, you can define it in different way. Theorems. Theorems is some of the deductions, okay, some of the reduced, right, from the laws, okay, from the laws. Okay, laws is the basis. Theorems is some tricks. Now, we one by one talk about the concepts. First, the voltage. Okay, the voltage can also be called as electromotive force. In short, electromotive force. Electromotive force more understandable because the voltage used to represent the force that to move the charges, electrical charges. Okay, so suppose we have an electric charge. It is the voltage that can push the electric charge move. So electromotive force. It is an expression for the electric potential or potential difference. Okay, if an electric path is provided between the 2 points with a voltage, electric charge will flow through this path. Okay, once again, the voltage is used to push the electrons moves cross through cross to terminals. Okay, so that's why we call electromotive force. In many books, they use the electromotive force to represent the voltage, which is more understandable. When we talk about potential, you know the voltage potential, gravity potential. Okay, gravity potential. So here we have an electric potential. Okay, so we have the high electric potential. We have low electric potential. The difference between them, we call it potential difference. And the difference between it, we call it voltage. So voltage is potential difference, not gravity. So you have the gravity potential, higher potential, and a high position, lower potential, and lower positions. The potential difference, okay, is a kind of energies. The potential gravity potential difference is a kind of the mechanical energies. The electrical potential difference is a kind of electrical energies. The electrical energies acts on the electrons. The gravity energies acts on mass objects. Any objects with mass okay, be okay, a gravity potential. That's the difference. So for your good understanding here, so I would like to write down, okay, two comparisons. Okay, so now actually, although the electricity is not right, is visible, you can compare this to gravity potential acts on objects with mass. Electrical potential acts on electrical particles. So electric particles, okay, they may have no mass. It doesn't matter about the mass. Okay, the push that moves. Okay, so that's the difference between them. But you can use in the same right, okay, logics to understand them. Okay, so for the voltage, we usually, when you read some books, we usually use in the V voltage, E electromotive force, or lowercase v and E, okay, to represent the voltage issues. The standard unit for the voltage internationally is the volt, okay, which is 1 volt. 1 volt, okay, is the volt, okay. In short, is the V. Now, what does it mean by 1 volt? So this is another definitions. Okay, not ask me why, but this is just okay, agreements between the okay, researchers. 1 volts is the electromotive force, okay, electromotive force required to drive 1 coulomb of electrical charge, okay, pass through a specific point in 1 second. Okay, 1 volt is the electromotive force that are required to push 1 coulomb of the electrical charge, goes through 1 point in 1 second. 1 coulomb goes through 1 point in 1 second is 1 amperes current. Okay, later on we will talk about this one. Look, so this is definition of it, 1 volts. You know that each electron, okay, has very small, each electron has 6.24 times 10 minus 18 power Coulomb charges. Okay. Okay. Currents. Now, what does it mean by currents? Exactly speaking, electrical currents. Okay, so to make things be clear here, that here the currents, we mean the electrical currents, okay, electrical currents. In practice, sometimes we also, for the streamer, for the river okay, flows, we also the word current. And in the high sky, we have the air current. Okay, so here the current means the electrical currents. The current is a flow of electric charge carriers, usually electrons or electro-deficient atoms. As I just mentioned that the inside any materials that consists of atoms, right? Including my human being's body. So any objects in this universe consists of the atoms. The atoms consists of electrons surrounding the nuclear. Nuclear. Okay, so the electrons negatively charged. It is movable. The nuclear not move. Okay, it is positively charged. Okay, so that's why we said electrons moves. So we're using the I to represent the currents in practice. Why using I don't know, but they use it. The first one proposed to use the I to represent the current. Okay. The standard unit is the amperes. Okay. So you can use the ampere, you can use the A, okay, to represent it. What does it mean by 1 amperes? Actually, we just talked in previous slide. 1 ampere represents 1 coulomb of electric charge moving past a specific point in 1 second. Okay, in 1 second. Okay, so as I just mentioned that the current directions, in practice, the current direction itself, it doesn't matter. Okay, so the positive charge go through, okay, a direction is defined as the physical directions of the currents. But in practice, the movable electrons, okay, is negatively charged. Okay, so this is just for the descriptions of the functions, descriptions of the conventional use, okay, in the mathematical formulas. It doesn't matter about the current directions in practice for in terms of power consumptions. Okay. Similarly, the resistors. Now, how we got the resistance? First, the medium resistance. Resistance is the opposition that a substance offers to the flow of the electric currents. So when there is a current go through a given object, substance, conductors, so they get some of the blocks from the substance. So it is these blocks against the electrons that getting the energies onto their substance. Okay, understandable. So when the electrons go through some of the objects, so there are some parts of the objects that try to block the move of the electrons. So this blocking process, getting energies from the electrons onto the subjects. So this is the consuming of the electricity. Okay, just like people's running into your run into you, and you block that person's. So that person's running energies, okay, get onto your bodies. You falling down. That people's stopped running and you falling down. You get the energies. So electricity can transfer energies onto substance in the same way, although invisible, but the same way. Okay, it is the charge carriers electrons by slow down their movements to pass their moving energies onto the substance. Okay. Now you should understanding that the electricity is just like mechanical issues. Although it is invisible, but it is the electrons moving there. It is too small for us to move to look. Okay, but you using a microscope, right? You can look the movements of electrons. The human being's eyes cannot look the moves, right? Okay, the symbols used to represent it is the R, and the standard unit is the ohm. Now, problem is that the how to define ohms. Okay, so simply speaking, for a given substance, if you apply 1 volt across this substance and you get 1 amperes go through these subjects, then we say this substance has 1 ohms resistance. Very simple. Okay, very simple. That means, so 1 ohm equal to 1 volt over 1 ampere. Look, so you apply 1 volt cross 1 ohms, getting 1 amperes. Since the resistance is the opposition force, block the voltage. So, of course, the larger of the resistance, the smaller of the current. The smaller resistance, the larger of the currents with the same voltage. That's the Ohm's law. So you look, the Ohm's law comes from the definition of the voltage, current, and resistance. Nothing but a definition. Okay. So it it is not So it's not a mystery. It's just based on the basic logic, right? So that's the so-called Ohm's law. Okay. Now, since we talked about resistance, now what is the characteristic resistance? The resistance used to represent the characteristics of substance. Now here, sorry, as I talked about that the resistance is opposition, okay, opposition against the flow of the currents. Now imagine for a given voltage along a given conductors, the longer of the conductors, the bigger of the blocking force. Just like a river, the longer of the river, the larger of the friction force, okay, to the flow of the water. Similarly, the wider of the river, the smaller of the force to block the flow of the water. Similarly, for the conductors, the bigger of the cross-sectional area, the smaller of the resistance. Okay, therefore, for a given materials, if we know the so-called resistivity, what does it mean by the resistivity? Okay, first, the resistivities. The resistivities is the resistance of a substance with a cubic meter volume. Get a point, right? So 1 meter is long with a 1 cross meter, okay, 1 square meter cross sectional area, 1 meter is long. So the resistance of this, okay, block, okay, a cubic meter volume of substance, the resistance, resistivities. Then if you have a conductors, which has L meters long with a cross-section area, say A square meter, L meters long, A square meters cross-section area with a resistivity rho here. Then the total resistance of these conductors can be estimated by the resistivity times the length L over the cross-section area. Pay attention to the unit of it. This is the first issues. The second issues, since the resistance is the opposition of the substance against the flow of the electrons. So the temperature affects the substance performance, therefore affect the resistance. You know, the higher of the temperature, okay, the more boron activities of the laboratory of the objects. Okay, you know that the temperatures determined by the molecular movements, right? So any materials, the molecule, right, movements, the higher temperatures, molecule moves, right, vibrations, molecule vibrations. Okay, we call it a boron, okay, movements. Okay, the bigger of the boron movements. So this boron movements, okay, this molecule movements, okay, making the resistance be bigger. What does it mean? For examples, if you right stand on the road, if you stand on the road, try to stop someone's running. You just stand there, no movements. You stand there, no movements. Just try to block the people's movements. And then when you move, right? Then you move your bodies, okay, left and right, left and right. And you try to block the people's moving. So then you have a little bit bigger, okay, force, bigger capabilities to move the peoples, right? To stop the peoples, okay? Because you are moves left and right, left and right. So you block the peoples in bigger areas. Similarly, when the temperatures be higher, that's the molecules inside the materials, they moves. So they can block the electrons, here, there, aware. So they have a big resistance. Get it, Mom? Okay? So that's the meaning of it. Actually, that's truth. Okay? So therefore, the higher the temperatures, the bigger the resistance. So different materials have different performance, but here we simplify it into a linear relationship between the resistance at different temperatures. Suppose objects or conductors has a resistance R0 at temperature T0, and the materials has a temperature coefficient alpha, or we say A alpha, okay? So which represent the resistance changes, okay? Resistance changes, okay? Change, right? The resistance multiplier, okay? Resistance multipliers, okay? When the temperatures, okay, change 1 degree change, right? 1 degree change. Okay, so the alpha here is the temperature coefficient of the resistance at the temperature referred to temperature T0. So if you measure the resistance at T0 is 1 ohms. And okay, when the temperatures be okay, T, you got another values. Okay, so that resistance difference over the temperature difference is the temperature coefficient at temperature T0. Okay, that's the meaning of it. Okay, so the resistance of the conductors at a temperature T can be estimated like this. Okay, like this. So this is the temperature coefficient and T0, okay, and this is the temperature T, and this resistance and temperature, okay, T0, and this resistance and temperature T, Okay, when the temperatures increase, positive values difference here, this is always positive and larger, okay, larger. Okay, so now you're understanding that the resistance of a conductor is not a constant. Okay, so resistance of a conductor changes with temperature. That's the points of the Formula 2, okay, which will be tested, examined. Okay, also we have exercise on these points later on. Okay, I will post an exercise on the Blackboard for you download to have an exercise of it. Now, Ohm's law. Ohm's law is the mathematical relationship among the electric current, resistance, and voltage. Simply speaking, the resistance is the voltage over currents for a given component. Ohms, volts, amps. Okay, amps. Now, let's looking at a given circuit as an example. Suppose we have a batteries that supply voltage to a resistors. In practice, we can measure the voltage across the resistor. Look, so measure the voltage across the resistor using a voltmeter. And we can using the ammeter measure the current through the resistors. Then the voltage over current is the resistance of this resistor. But look at here, for a voltmeter, since we use it to measure voltage across the resistor, we should making the voltmeter's internal resistance much larger than the resistance of the resistor. Otherwise, we have current go through the voltmeters. In practice, because the voltmeters has a very big internal resistance in comparison with the resistor. So you have very little current go through of it. So 90.9% go through resistors. 0.01% go for voltmeters. Anyway, we cannot measure the accurate absolute voltage across a resistor at all. Okay, theoretically, we cannot do that. So that's the engineer issues. Similarly, now you look, the ammeters now is in series to the resistor, but actually it also series to the voltmeters here. So the ammeters measure the total current go through the resistor and a voltmeter. But as I just mentioned that, okay, the large internal resistance making the current go through voltmeters very small. So the current measured here, 99.9% is the current go through resistors. On the other side, the ammeter should have a very small internal resistance so that the voltage drops across the ammeters be very small. Look at here. So the voltage is the ohms times the amperes. So for the ammeters, if the internal resistance is big, the current times the internal resistance, that is the voltage drop across it. Okay, so it should have internal resistance, but the internal resistance should be small. Okay, so in practice, the internal resistance of ammeters can be ignored, while the in terms of the series connections, and the voltmeter circuit can be seen as an open circuit. So as I just show you here, so the ammeter usually has a very small internal resistance in comparison with the resistors, and voltmeters has a relatively larger internal resistance in comparison with the resistors. In other words, you should choose, if you try to measure the resistors, you should choose the voltmeters, okay, that has a relative larger internal resistance to the resistors. You should choose the ammeters that have a relatively smaller internal resistance in comparison with the resistors. Otherwise, the errors will be very big. In practice, when you analyze the circuits, so the ammeters can be seen as a short circuit. That means the internal resistance can be ignored. And the voltmeters can be seen as an open circuit. That means there's open here, just like opened, right? Just like open, okay? And ignored. That's the meaning of it. But it just used to read the voltage. Okay, that's the meaning of it. Okay, in practice, as an engineer, you should pay attention to it. But when someone asks you to okay, so if you try to analyze the errors, you might bear in mind that the ammeter has a small internal resistance and the voltmeter has a large internal resistance. You might. Okay, and that's why when you're doing experiments, you got the powers, okay, measurements, current measurements, voltage measurements with errors. So the errors be bigger, -1, errors be +1. You should know how to analyze of it. Bear in mind that there are some internal resistance of the voltmeters. There are internal resistance of the ammeters. Okay. So I just remind, highlights these 3 points. In practice, we're using these laws. Okay, so we will talk, right, these 2 examples during tutorials, okay, which concern about Ohm's law, which concern about the change of temperatures of the conductors, okay, and so on. And lastly, here we talk about power issues. So power, how to define the powers? Okay, so the electric power associated with a complete circuit, that closed loop, or a circuit component represents the rate at which energy is converted from electricity energy into some other energies, like the heat, mechanical energy, or energy stored in electric fields or magnetic fields. Later on, we will talk about it. Okay. Anyway, in this moment, for a DC circuit, we just have resistors. The resistor used to represent the energy consumers. The consumers may be a heat, may be a mechanical energy movements, may be energy storage in electric fields, may be energy storage in magnetic fields. Anyway, so we're using the real resistance to represent it. So then we have a so-called voltage cross-it that mirrored by the voltmeters. We have the current through it that mirrored by the ammeters. Then, so if the voltage be 0, then the powers be 0. If the current be 0, then the powers be 0. Okay, that's it. Okay, so we get logic. If the current be 0, then the power be 0. If the voltage be 0, then the power be 0. So the power is the products of the voltage and currents. Okay? Very simple. This is a logic. This is logic. So that's the logic. You can work as a right logic. Okay, you can get some new laws, right, like this. So that's why we define the power is the product of voltage and currents. Okay, so introduce. Okay, we have the Ohm's law here. So by taking the Ohm's law, we can find out that the powers okay, so the power go through a given resistance proportional to the I square, current square, and proportional to voltage square over the R. And is the product of the current and the voltage. Now, look at this term. For a given voltage, the smaller resistance means bigger powers. This is a little bit different from your existing concept in your mind, right? Use your mind. Okay, so for given voltage, smaller of the resistance, bigger of the powers. Bigger the powers. For a given currents, larger of the resistor, larger of the powers. But in practice, we usually keep the voltage no change, rather than the currents, right? The current actually has been determined by the voltage over the currents, voltage over the resistance. Current determined by the voltage over the resistance. Okay, and the resistance is a relative constant to represent the characteristics of a given colors, although it is changing with the temperatures. So resistor representatives of the user. Voltage representatives of the source. Current representatives of the power flow. And actual power it depends on the products of the voltage and the currents. That's the power relationship. So now it is easy to remember of these formulas because you must know the logic of it. When the current be 0, the power be 0. When the voltage be 0, the power be 0. Therefore, the power is the product of the voltage and the current. Nothing but like this. And meanwhile, we have the Ohm's law that the current cross through a given resistor R depends on the voltage, right? Cross it. Okay, the voltage over the resistance is the current. That's the Ohm's law. So based on the Ohm's law, based on the power definition, we have many other changes of these two. Okay, change these two. So network of the resistance. We have a quick look at resistance. So in practice, we may have several loads in series. When you have several loads in series, namely resistance 1, R1, R2, R3 in series, then each series, they share the same currents. So they have the same currents. They share the total voltage. So the total resistance is the total voltage over the total currents, and the total voltage has been shared by each of the resistance. So each of the resistance has a voltage drop. That's the current. Okay, that's the current IR1. Okay, current IR1. Okay, Ohm's law. So the resistance 1 getting a voltage V1, resistance 2 getting voltage V2, and so on. Now we can separate them because the current is the same. When in series, current is the same. Okay. Okay. So therefore, the total resistance, you can prove the total resistance is the sum of all the resistance. That's it. Now, in parallel case, so in parallel case, the common voltage used. That means the voltage across R1, R2, R3 the same. We call the same. But the current go through R1, R2, R3 are different. You know the Ohm's law. Okay. So that the voltage, total voltage over the total resistance. So it's the total currents. It's the total currents. And the total currents is the currents 1 here, currents 2 here, currents 3 here, and so on together. So current 1, current 2, current 3, just like a reverse branch, right? Okay, branch 1, branch 2, branch 3, branch 4, and so on. The current added together is the total current. And the total current is the total voltage over the total resistance. Now, each of the current 1 is the voltage over R1 because the voltage is the same, common voltage used. So the voltage 1 over R1, voltage 2 over R2, voltage 3 over R3. Voltage 1, 2, 3 the same is the V. So that's why we have this, okay, 1. Okay, so the total resistance is related to the individual resistance with these formulas. Okay, while that in the series one, okay, we have this one. Okay, we have this one. Okay, so this is the network issues. I think this is not right so difficult. This is also is the logical issues. This is the applications of the Ohm's law to individual components and to in the total components. Okay, to Ohm's law application to individual and the total components. Okay, so we got the formulas here for series connections and for parallel connections. So many nodes in parallel, making the total resistance become smaller. That's the things of it. Okay, so we stopped here today for these lectures. And next Tuesday morning and next Tuesday afternoon, we have 2 sessions of tutorials, the same, okay, talking about the same issues. Okay, so wish you all can attend that tutorials on times. See you next times. Take care about the weekend. Bye-bye.